The construction of a 15-meter span Macrete FlexiArch road bridge in Shropshire, England, showcases an innovative approach to modern bridge building. The FlexiArch system, developed by Professor Adrian Long from Queen's University Belfast, mimics the ancient principles of masonry arch bridges but employs contemporary materials and techniques. This flat pack solution, commercialized by Macrete Limited, offers a unique blend of traditional engineering principles with modern precast concrete technology. The Macrete FlexiArch system is essentially a pre-engineered and prefabricated structure, composed of precast concrete units that are delivered to the site in a flat configuration. During the construction process, the flat pack segments are lifted into position and undergo a transformation due to their specially designed wedge-shaped geometry. As the segments are lowered onto the abutments, their own weight causes them to assume the desired arch form without the need for complex falsework or temporary supports. This technique not only simplifies construction, but also enhances efficiency and reduces the time and cost compared to conventional masonry arches. FlexiArch bridges can be manufactured for spans ranging from 3 to 15 meters, and for longer requirements, multiple arches can be combined to extend the bridge width. The Shropshire project employed this system to construct a 15-meter span road bridge, marking one of the longer applications of this innovative method. This approach allows the new structure to maintain the visual appeal and durability characteristics of traditional masonry arches while incorporating modern structural benefits like enhanced load distribution and reduced maintenance requirements. The replacement of the Easthampton Manhan River Bridge marks a significant milestone in infrastructure improvement for the community. Located in Easthampton, Massachusetts, the bridge plays a critical role in local connectivity and commerce. Its replacement involved the adoption of an innovative construction approach known as the Accelerated Bridge Construction (ABC) technique. This modern method enabled a quicker and more efficient bridge building process, minimizing disruption to local traffic and the environment. The Massachusetts Department of Transportation, MassDOT, decided to use the Accelerated Bridge Construction (ABC) technique for this project. ABC has become a popular choice for modern bridge construction because of its ability to shorten project timelines, reduce traffic interruptions, and enhance safety. This method typically involves the off-site manufacturing of major bridge components, which are then assembled rapidly on-site. For the Easthampton Manhan River Bridge, one of the main tasks involved the installation of deck bulb T-beams, a vital structural element of the new bridge. The deck bulb T-beams are large, precast concrete beams that provide both strength and stability. In this case, each beam measured 93 feet in length and weighed approximately 100,000 pounds. These beams were specifically chosen for their capacity to span wide gaps while providing a solid deck for the bridge structure. On the day of the installation, the beams were brought in from Vermont, where they were precast and prepared to the project's exact specifications. The transportation phase involved loading each beam onto specialized tractor trailers designed with platforms that could securely hold the massive load during the journey. Upon arrival at the bridge construction site, the beams were lined up in sequence for installation. It was crucial that each beam remained securely positioned on its platform until it was lifted by the crane. This step required a lot of coordination and planning, ensuring the beams were in the correct order and ready for the installation process. One of the central features of this replacement process was the use of a large crane. The crane, which was a significant investment and logistical element of the project, played a pivotal role in moving and positioning the heavy beams. Its sheer size and lifting capacity enabled it to carefully maneuver each beam from the trailer, over the river, and into its designated place on the bridge structure. The installation began at around 7:30 in the morning, with the placement of the first beam. As with any large-scale construction project, the initial beam placement replacement took longer as the team had to make precise adjustments and measurements. Ropes were used to help guide the beam into place and keep it steady as the crane carefully lowered it into position. The workers' attention to detail during this step was critical, ensuring the alignment and placement were accurate, providing a solid foundation for the rest of the beams. Despite challenges like rain showers in the afternoon, the team continued their work. As the day progressed, the workers gained confidence and efficiency in their tasks. By the time the 7th and 8th beams were ready to be installed, the process had become much smoother and faster. Each beam was carefully positioned and measured before being secured in place. This efficient approach was a key benefit of the ABC technique. What would have traditionally taken weeks or months to accomplish was completed in just one day. By reducing the construction timeline, the team minimized disruptions to the community and surrounding environment, allowing for a more seamless transition to the next phase of the project. By the end of the day, all 8 beams were successfully installed, marking a significant advancement in the bridge replacement project. With these critical structural components in place, the bridge had quickly begun to take shape. The success of this phase showcased the effectiveness of the ABC technique in bridge construction, demonstrating its ability to streamline operations and deliver results in a much shorter time frame than conventional methods. Although the major task of installing the beams was completed, additional work remained to be done, including the construction of the bridge deck and other finishing touches. However, the project was well on its way to completion, and the main structural component that typically presents the greatest challenge was successfully tackled in a single day. The replacement of the Easthampton Manhan River Bridge is a testament to the advancements in bridge construction techniques. By leveraging the accelerated bridge construction technique, MassDOT not only reduced the construction time significantly, but also enhanced safety and efficiency throughout the process. The Senqu River Road Bridge, located in Mount Moroosi, Lesotho, is a significant infrastructure project aimed at connecting communities and enhancing transportation over the Senqu River, which is known as the Orange River after entering South Africa. This river originates from the Maluti Mountains and is one of the few perennial rivers in South Africa. The Senqu River's unpredictable rise in water levels due to its vast catchment area presented challenges that required innovative monitoring solutions during construction. The Senqu River Road Bridge is designed as a steel composite structure with a total length of 142 meters and a width of 11 meters. The bridge design consists of 2 abutments and 3 piers, which serve as the main support structures. Steel girders form the core structural framework of the bridge, which are complemented by a reinforced concrete deck that provides a strong and durable surface for vehicular and pedestrian traffic. The choice of a steel composite structure offers significant advantages, including strength, durability, and the ability to withstand fluctuating water levels and strong river currents. The concrete deck provides a smooth, load-bearing surface, making it ideal for both pedestrian and vehicular use. Prior to the construction of the Senqu River Road Bridge, local residents relied on row boats to cross the river, a method that was both time-consuming and hazardous, especially during the rainy season when water levels could rise unpredictably. The construction of the bridge is expected to have a transformative impact on the daily lives of these residents, enabling safer, faster, and more reliable transportation. The completion of this bridge will not only facilitate easier access to goods, services, and emergency aid, but also promote economic growth in the region by improving connectivity between Mount Moroosi and surrounding areas. The Senqu River, with its vast catchment area, experiences unpredictable fluctuations in water levels, making construction over the river a complex task. The project has employed advanced monitoring techniques, including time-lapse systems to provide continuous updates on water levels and construction progress. High-definition imagery is captured daily, offering valuable insights to the project's stakeholders and enabling proactive responses to any emerging challenges related to water level rises or other potential risks. The time-lapse monitoring system plays a dual role, ensuring the safety of workers during construction and providing transparency to the project's client. By offering real-time updates on the river's conditions, these systems help in making timely adjustments to the construction schedule and in safeguarding the structural integrity of the bridge during the project's critical phases. Upon completion, the Senqu River Road Bridge will not only replace the need for rowboats, but will also open new opportunities for trade, education, healthcare, and social interaction for local communities. The construction of the new Olifants River Bridge in the Western Cape, South Africa, forms part of a broader effort to upgrade the N7 highway. This strategic project was deemed necessary due to the limitations and deterioration of the existing bridge, which was originally built as a railway bridge in the 1970s. Over time, the old structure showed signs of disrepair, including noticeable cracks, which raised concerns about its capacity and safety. Instead of attempting to widen the old bridge, engineers opted to build a completely new one, designed to better accommodate the current and future traffic needs. The new bridge is an arch-type structure, spanning the Olifants River within the boundaries of the West Coast District Municipality. The South African engineering firm Oricon was responsible for its design. The central feature of the new bridge is its primary arch span, which stretches 96.6 meters. This design choice not only enhances the bridge's aesthetics, but also addresses structural efficiency, allowing for a more robust load distribution. In total, the bridge spans 168 meters. The main arch section is complemented by additional spans on both ends, 3 spans of 14.6 meters each on the northern side, and 2 spans of 13.8 meters each on the southern side. This combination of spans results in a stable and balanced structure that can withstand the dynamic forces imposed by both traffic and environmental factors. The deck of the bridge is built using a reinforced concrete continuous twin-spine solid slab, reinforced further with diaphragm beams at each pier. This design ensures rigidity and minimizes deflection under load. The arch itself is split into 2 parallel ribs with connecting beams at each pier. This forms a ladder-like structural configuration, which enhances stability and provides greater resistance against bending and torsional forces. The bridge is supported by piers, which are designed as twin-column-type piers that integrate seamlessly with the arch. The piers feature concrete hinges located near the deck, allowing for some controlled flexibility in response to various stress loads, such as temperature variations and shifting weights. This innovative use of hinges also helps to mitigate the risk of structural cracking and extends the bridge's lifespan. The bridge's abutments are designed as solid cantilevers with return walls, ensuring a strong anchorage for the entire structure. Additionally, the bridge's width of 12.25 meters allows for a 2-lane configuration, accommodating 2 lanes each with a width of 3.7 meters. It also includes 1-meter-wide shoulders on each side and a 1.5-meter-wide sidewalk, catering to both vehicular and pedestrian traffic. For safety, precast concrete F-shaped parapets of 1.1 meters high are installed. These parapets are specifically designed to reduce the impact of vehicle collisions and prevent vehicles from veering off the bridge. The entire structure is founded on shallow rock, providing a stable and durable base that can handle the weight and stresses of the bridge over time. The Greenfield Bridge, officially named the Beechwood Boulevard Greenfield Bridge 2, stands as an enduring symbol of Pittsburgh's evolving infrastructure. Connecting the neighborhoods of Greenfield and Squirrel Hill over the valley known as 4 Mile Run, the bridge spans the bustling Parkway East, I-376. The bridge's history traces back to the 19th century, with each iteration reflecting advancements in engineering and changes in the city's needs. From a simple wooden structure to its current steel design, the Greenfield Bridge tells a story of collapse, rebirth, and resilience. The original crossing at this location was constructed in 1891 as a wooden deck truss bridge. At that time, it was commonly called the Forward Avenue Bridge due to its location. The bridge was approximately 378 feet long and 30 feet wide, connecting what would eventually become Beechwood Boulevard to Greenfield. Its creation marked a pivotal point in developing Pittsburgh's transportation network. In 1898, Beechwood Boulevard was officially extended to end at the bridge, transforming the route into a scenic 9-mile carriageway from Shenley Park to Highland Park. This extension, in turn, led to the bridge being renamed the Beechwood Boulevard Bridge. However, the bridge's early years were marred by structural problems. Over time, its wooden construction deteriorated, requiring multiple repairs. The culmination of these issues came on June 18, 1921, when the bridge collapsed. The bridge had already been closed to vehicular traffic due to safety concerns, but was still accessible to pedestrians. Fortunately, when the collapse occurred in the afternoon, no injuries were reported, although 5 pedestrians narrowly escaped the incident. This event underscored the challenges of maintaining infrastructure in a growing industrial city. In the wake of the original bridge's failure, the city replaced it with a more durable structure, a concrete arch bridge. Construction began soon after the collapse, and the new bridge was completed in 1923. Officially named the Beechwood Boulevard Bridge, but colloquially known as the Greenfield Bridge, this open spandrel concrete arch structure became a familiar landmark in the city. Designed by Charles M. Reppert, the bridge stretched 466 feet in total, with a main span of 274 feet. It featured decorative elements such as ornamental entrance pylons, light standards, and urns, giving it a unique aesthetic appeal. The bridge's construction was part of a broader initiative by the city of Pittsburgh to build several similar structures during the 1910s and 1920s, although by 2022, only one, the Larimer Avenue Bridge, remained. Over the decades, the bridge faced increasing structural problems. By the 1970s, concrete chunks began to fall from the structure, prompting a temporary closure and a subsequent rehabilitation effort costing $2.1 million in 1980-81. Despite these repairs, the bridge's condition continued to decline, and safety netting was installed in the 1990s to catch falling debris. This measure proved insufficient when more concrete fell soon after, leading to accidents on the Parkway East and injuries. Although city officials suggested vandalism as a possible cause, the recurring incidents pointed to the bridge's decaying state. The situation reached a crisis point in 2003 when another incident involving falling debris injured a driver. While investigations suggested that the debris was not from the bridge, the city erected a bridge under a bridge as an additional safety measure. The Greenfield Bridge's state of disrepair turned it into a national symbol of America's infrastructure issues. Media coverage on shows like 60 Minutes and Last Week Tonight with John Oliver amplified this image, highlighting the aging infrastructure that threatened public safety and required immediate attention. The bridge's decline culminated in a carefully planned demolition in December 2015. At 9:20 a.m. on December 28th, the Greenfield Bridge was imploded, closing a chapter in the bridge's long and troubled history. Despite efforts to protect the underlying highway with a layer of dirt during the implosion, damage to the outbound lanes delayed reopening. The inbound lanes of I-376 were cleared and reopened by December 31st, a day ahead of schedule, marking a milestone in the project. Following the demolition, the city embarked on constructing a new bridge to meet contemporary safety and traffic demands. The new Greenfield Bridge, officially named the Beechwood Boulevard, Greenfield Bridge 2, was opened to traffic on October 15, 2017. Designed by HDR Inc., the replacement bridge costs $17.5 million to build and features significant improvements while paying homage to its predecessor. The design of the new bridge retains elements of the original structure's appearance, preserving a sense of continuity and respect for the site's history. Many of the original bridge's stone ornaments were restored and integrated into the new design, offering a nod to the past while embracing the future. Additionally, the new bridge boasts wider lanes and sidewalks, as well as a dedicated bicycle path, reflecting modern standards and the growing importance of multimodal transportation. A key design feature of the new bridge is its painted green steel elements, symbolizing the connection to the Greenfield community. This choice adds a visual link to the neighborhood and provides a subtle reminder of the bridge's namesake. Pittsburgh's Beechwood Boulevard, Greenfield Bridge has long served as a significant gateway to the city and a crucial link between Greenfield and Squirrel Hill neighborhoods. However, after nearly a century of service, the bridge fell into disrepair and became emblematic of America's crumbling infrastructure. Featured on 60 Minutes as a symbol of neglect, it was clear that the bridge needed urgent intervention. City officials faced a tough decision whether to rehabilitate the aging structure or replace it entirely. The original Greenfield Bridge, constructed in 1922, had a concrete arch design that was both functional and elegant. Over the decades, however, the bridge faced significant wear and tear. By the early 2000s, spalling concrete revealed corroded steel reinforcements, and earlier renovations had stripped the bridge of its classic architectural features. The once stately bridge had become wrapped in safety netting, meant to catch falling debris, and a bridge under the bridge had been constructed to protect passing motorists. Despite these stopgap measures, it became evident that the bridge's days were numbered. The task of revitalizing the Greenfield Bridge was no small endeavor. Given its iconic status and the challenges posed by its location over a major highway, Interstate 376, Pittsburgh city officials aimed not only to preserve the bridge's historic essence, but also to bring it up to modern standards. HDR Inc., the design firm selected for the project, had extensive experience with local infrastructure, having previously worked on other Pittsburgh bridges, such as the South Millvale Avenue Bridge. Their familiarity with the region and commitment to preserving iconic landmarks made them the ideal choice for this project. The $17.5 million project, awarded to HDR, aimed to design and construct a replacement that would honor the original bridge's character while meeting 21st century transportation needs. Given the bridge's location at the entrance to Schenley Park, Pittsburgh's second largest park, the design needed to serve not only as a transportation facility, but also as a scenic and inviting gateway. From old to new, the rebirth process, the journey to rebuilding the bridge, began in 2009 with a comprehensive inspection of the existing structure. An alternatives analysis study was conducted to explore rehabilitation options versus a complete replacement. Ultimately, the decision was made to replace the concrete arch bridge with a new steel arch structure. Key to the project's success was the safe and efficient demolition of the existing bridge, situated above one of Pittsburgh's busiest stretches of highway. During the design phase, the HDR team worked closely with local contractors to brainstorm solutions for the bridge's implosion. They concluded that a Christmas week closure would be the least disruptive time to carry out the demolition. The implosion occurred in December 2015, with crews demolishing the concrete arch using explosives. The city successfully cleared the rubble and reopened Interstate 376 within 5 days, ensuring that the highway was operational before New Year's Eve. The swift and efficient demolition minimized disruption to the city, allowing Pittsburgh residents to ring in the new year with their infrastructure intact. The city and design team paid careful attention to the aesthetics and functionality of the new bridge. The replacement bridge was crafted to preserve elements from the original, incorporating stone urns, decorative pillars, and a stone obelisk into the design. Form liners and decorative fencing and lighting were added to restore the bridge's historical grandeur and maintain its role as a majestic entrance to Shenley Park. The color of the steel elements was selected to reflect the Greenfield community and create a visual connection to the neighborhood. In addition to its visual appeal, the new Greenfield Bridge also features a wider than normal sidewalk and designated bike lanes, making it a more accessible and welcoming structure for pedestrians and cyclists. The improvements allowed the bridge to function not just as a crossing, but as a community space that accommodates modern, multimodal transportation needs. The bridge reopened in October 2017 and has since been recognized for its excellence in design and construction. Its successful transformation demonstrates Pittsburgh's commitment to preserving its historical landmarks while meeting contemporary infrastructure standards. The project's careful blend of state-of-the-art engineering and historic preservation highlights the city's dedication to its architectural heritage and modern progress. The Beechwood Boulevard Greenfield Bridge is more than just a transportation link. It is a vital part of Pittsburgh's landscape and history. Through innovative design, thoughtful preservation, and careful planning, the bridge's rebirth has re-established it as both a functional gateway and a symbol of resilience. The project serves as a model of how cities can honor their past while investing in their future, ensuring that treasured landmarks continue to play an essential role in the community.